Let's now take a look at the idea of the sampling distribution, specifically for the sample proportion. The concept that we just looked at in terms of the sampling distribution for the sample mean will carry over to the proportions. It's the same idea. The CLT also applies to the sampling distribution of the sample means, or sample proportions. This should be of, not if, minor typo there. The CLT tells us that for large enough n, which is the sample size, the distribution of the sample proportions will be p hat, the sample proportions will be distributed normal, but the mean will be pi, this is mu, and the variance will be pi times 1 minus pi over n. This is the variance. Now I'm going to subscript this. This is the mean of the sample proportions. This is the variance of the sample proportions. Okay, remember, whenever we use this notation and in those parentheses, we're talking about our normal distribution, something being distributed normally. The first parameter is always the mean. It's the mean of whatever the random variable is. The second parameter is always the variance. So based on this idea, you already know what to do with it. If I start asking probabilities based on proportions, once I have these values, I can answer any probability that anybody wants to ask me. Okay, the requirements for applying the central limit theorem to sample distribution for sample proportions is different from what we saw from the sample means. The reason being is that when the sample means, we said we need the distribution to be normal to begin with, or large enough sample size for the CLT to apply. We start talking about proportions. What could it mean for the population to be normal? Well, the population is going to be a bunch of ones and zeros. How can that be normal? The reason I say ones and zeros, or yeses and nos, the population is actually going to be nominal. If you're looking at a proportion, you collect data, and when an object has whatever it is you're looking for, you check mark yes. Or you may record a 1 for a yes and a 0 for a no. How can yeses and nos, ones and zeros be normal? That doesn't make any sense. So the idea of the population, the parent population that we sampled from being normal, has no meaning. Also, the idea of large enough n is slightly different from what we saw as the CLT applies to the sample means. For the sample means, we said if n got to be at least about 30, then things are pretty good. Here, there's three things that we need to show. The first, we need n to be at least 20. We also need n times pi to be at least 5. And we need n times 1 minus pi to be at least 5. We need all three of these in order to feel pretty comfortable that the sampling distribution of the sample proportions is normal. Now, personally, the 20 is not all that important. If I have these two, if these two are good, if I can show both these apply, then 20 is not really that big of a deal. A, B, and C, n times pi and n times 1 minus pi, those are the biggies. If those happen, then we're in good shape. Okay, let's take a look at an example that actually works something out. Here's a scenario. Harley-Davidson motorcycle make up approximately 14.3% of all motorcycles registered in the United States. Suppose you're planning to conduct a survey of motorcycle owners with a sample size of 500. Well, let's see what this scenario gave me. I haven't asked a question yet, but what did this scenario give me? It gave me a sample size of 500, so I know that n equals 500. And it says that 14.3% is what the Harley owners make up of all motorcycles. That sounds like pi to me. Sounds like pi is 0.143. Describe and justify the sample distribution for the sample proportion. Well, it looks like p hat is going to be normal with a mean of 0.143. That's pi. And a variance of pi, 1.143, times 1 minus pi is 1 minus 0.143, divided by n, which in this case is 500. That's the variance. Why is this reasonable? Well, I need to check. First of all, n needs to be at least 20. It is. N equals 500. I really need n times pi to be at least 5. It is. 0.143 times 500. It's definitely more than 5. It's, see, 0.1. I'm just going to do it real quickly here. 143 times 500. That's 71.5. And then 0.14, I'm sorry, I need 1 minus 0.143 times 500. Well, that's going to be 500 minus 71, which is going to give me, what, 428.5. Yeah, check. These are definitely greater than 5. Now, notice what I did here. I didn't simply say, this is what I need to show, and leave it. I actually showed how it's true. This is what I need. This is how I said, yeah, it's true. You really need to report both of these. Now, how likely is it that at least 20% of your sample will be Harley owners? Well, this is saying what's the probability that if you did this, p hat would be at least 0.20. Well, if I draw a picture, the mean is going to be 0.143. 0.20 is up here someplace. That's the area I'm looking for. So I would use normal, CDF. I just justify the normality right here. I justify why this is reasonable. The lower bound is going to be 0.20. Upper bound is going to be E99. The means will be 0.143. The standard deviation is going to be square root of all of this. It's going to be square root of 0.143 times 1 minus 0.143 divided by 500. Now, I'm going to redo this radical because I want to make sure you understand all of that is under the radical. Take the square root of all of that. Whip that into your calculator and see what we get. All right, let's go to the calculator and see. I'm going to go to normal, CDF. Lower bound was 0.2. Upper bound is E99. The mean is 0.143. The standard deviation is square root 0.143 times 1 minus 0.143 divided by 500. Hit enter. And I get that probability is 1.3591 E negative 4. Or this is scientific notation. It's saying move the decimal over. It's about 0.1230 and a 1. That's what I'll report. So, if this is accurate, it's just 14.3% is accurate to begin with. It's not very likely you're going to take a sample that's representative of the population and get a sample proportion of at least 20. Notice this is really the same thing we did previously with the means. These are just numbers. Here's my mean, here's my variance. They're just numbers. It's a concept you need to make sure you grasp that. We're not talking about the proportions. So what we use to come up with the mean, or how we determine what the mean is, how we determine the variance is a little bit different is all. Now, suppose you completed the survey and you did find at least 20%. So you did this survey and you really did get 20% or more. Would you consider that to be unusual? And if yes, yeah, why? And if no, why not? Well, the answer would be, yeah, that's pretty unusual. Why? Because the probability is only 0.0001. See, what is this? This is tens, hundreds, thousands, 10,000s. This is saying that if I actually did this survey 10,000 times, that only one out of that 10,000 would I expect to see a probability of 0.20 out of random chance. That's chance error. I wouldn't expect that to happen. I mean, are you going to do the survey 10,000 times? I don't think so. So if it did happen, you say, wow, that really is unusual. Well, suppose it really did happen. And suppose that you were comfortable that your sample was reasonably representative of the population. So let's make the assumption here that you did everything right and you feel good about what you did. But this actually happened. You actually ended up with a probability of 0.0001. That happened. What conclusion might be able to draw? Well, what this is saying is that it looks like pi equals 0.143 that was reported is wrong. It appears that pi is greater than 0.143. I don't know what it is, but it sure seems like that proportion, 0.143, is probably going to be wrong. Okay, that's basically it with the proportions. That's the idea. You set up your sampling distribution. You specify the parameters, the parameter values, justify y based on the central limit theorem, and then calculate probabilities off of a normal distribution like you normally would. That's it.